It's a real pleasure to be here. I'm really enjoying this week. Well, it's a busy week, but it's a real pleasure to be here with all of you and to give my mini course. This is a talk which is formally independent from what I'm speaking about in the mini course, but I think it will serve as a nice introduction to what we're going to do tomorrow in the workshop. Okay, so I'll be speaking about Schubert calculus. And Gelfand-Zetlin polytopes. What I'll be speaking about is joint work with Valentina Kirichenko and Vladlen Timorin, who are both my colleagues from Higher School of Economics in Moscow. And I'll start with some motivation or some historical introduction on where did Schubert calculus come from? Well, the original set of problems people were interested in came from enumerative geometry. Enumerative geometry is a very old set of, could we say branch of mathematics or set of problems? But the first, probably the first problem on geometry and something which is pretty complicated dates back to the 2nd century BCE to Apollonius of Perga. He asked the following question: if you have 3 circles on a plane, in such a way that they were tangent to all 3 of them. So here you immediately see something like this, or maybe you can draw something like that. So at this picture, it's clear that there is like more than one, or maybe this will also do. So there are some possibilities that the circle, the tangency is from outside, like here, or from inside, like here. So the answer, well, the maximal answer you would expect, and of course this depends upon a configuration. If should I draw all 3 circles one inside another? Well, of course there would be no circles tangent to all 3. So so the question was to count the number of circles tangent to 3 ones. And the answer is, of course, it depends upon the configuration. And I think it was solved by Apollonius. He understood that the answer is less than or equal to 8. Well, let me put it like this: it can be 8, it can be less than 8, any number less than 8, except of 7. It's pretty strange but you cannot draw a configuration of 7 circles tangent to 3 given ones, but for 5 or 3 you can do it. Okay, so yeah, but this is not the kind of problems we're going to consider today. But still, it is a problem of enumerative geometry. It is asking for the number of geometric objects satisfying certain conditions, like tangency to something given, or let me pass to another problem, and I need to apologize to the workshop participants that they are maybe already fed up with this problem, but four-line problem. So suppose you have 4 lines in the space, and let's say C3, or you can say CP3, projective space, but it doesn't matter because you take 4 lines in general position. L1 to L4, and you're asking what's the number of lines meeting all 4 of them, like this. So yeah, so lines are in general position, so they are skewed to each other. And the answer is quite, well, it's not very obvious that the answer is 2, and well, at the first glance it's quite unclear how can it happen, because you probably would expect the answer to be either 1 or infinity or 0, but no, it's 2. And yeah, here's well, this, I think this is one of the problems which motivated Schubert for inventing Schubert calculus, or something what he called the calculus of conditions. It's 1870s, and there is a book where he considers a lot of numeric problems, and the approach which he proposed is as follows: that okay, so this is each of these conditions. Well, so you have four conditions, meaning meeting one given line, and then you can if you're considering conditions, you can sum them up or multiply. Multiplying means that you're imposing the conditions at the same time. Summing 2 conditions means that you impose either that or this condition. So like Boolean operations, and or. And here you have a condition to meet a line, and you want to find the 4th power of it. And here's how we are going to do it, as it was proposed by Schubert. Well, let's deform our configuration of 4 lines a little bit in such a way that these 2 lines would meet. And let's do the same with, so it's L1, L2, and it's L3, L4, and let's move them around and make them meet. Okay, and well, he said, you know, that it's pretty clear that the number of lines satisfying these conditions wouldn't change. It's also it is also this principle as the principle of continuity. It was actually due to some mathematician of the first half of 19th century. And this is a French mathematician who started his career in Russia. His name is Jean-Victor Poncelet. And his career was started in quite an extraordinary way. He was an officer of Napoleon's army marching towards Russia, and in one of the battles he was taken prisoner, And after the war, he spent maybe 2 years in somewhere in Russia, in Saratov. And he had not much to do, so he started doing math in his spare time, which he had many. Afterwards, after he was released and returned to France, he wrote a book which became like the foundation of projective geometry. And in Moscow, there is a Russian-French laboratory where French visitors can come to interact with mathematicians from Moscow. It is named after Jean-Victor Poncelet. So, okay, yeah, and after he returned to France, he made a very bright career. He became general. He was the director of École Polytechnique and renowned mathematician or specialist in mechanics, engineering. Okay, well, sometimes careers can be, be quite extraordinary. I'll mention another example a little bit later. So, so that's the principle of continuity proclaimed by Poncelet in the beginning of 19th century, and Schubert said that well, let's use this principle and let's deform our configuration. And principle of continuity tells us that nothing gonna change. Well, of course, it's a reasonable question why, but if you believe Schubert at this point, you'll see that the answer immediately is 2, because meeting these 2 lines means either passing through that point or lying in the plane spanned by L1 and L2. Same for these 2. So you have either this line, which is the first one, or the common plane, the intersection line of these 2 planes. So, well, let me draw it somewhere here. So here are the 2 lines, but the question still stands why it is true, and this question was stated by Hilbert on among his famous 23 problems. So Hilbert's 15th problem was to give rigorous foundation of Schubert calculus, because it worked, but no one really understood why. Okay, so so the Schubert calculus is, as it turned out to be later, some part of Schubert calculus is about computations in some cohomology rings, and well, or intersection theory. And this is well, the varieties you should consider for that are exactly those which this mini course is about, namely Schubert varieties and flag varieties. Today I'll be speaking about flag varieties. And, well, I'm only interested in flag varieties of type A. Okay, and this is as follows. So let me take an n-dimensional space. Today I'm going to work over complex numbers, but okay, this can be arbitrary algebraically closed field of 0 characteristic. And I'm taking, well, inside V, I'm taking complete flags. Namely, these are sets of nested subspaces. V dot, V naught inside V1, inside V2, inside etc. Inside Vn equals to Cn. And such a thing is called a flag. And the set of flags will be denoted as FL of n. And you see that on Cn you have the group GLN acting on it. So you act also upon flags. You can bring one flag to another, and this section is transitive. Any flag can be brought to, say, to your favorite flag. Well, my favorite flag is spanned by the elements of standard basis, E1, E2, etc., En. you can say that Vi is the span of E1, EI. Well, let's say W, and any flag can be brought to this one. Okay, so the stabilizer of this flag, so the flag variety is acted upon by GLN, and the stabilizer of a given flag is isomorphic to a subgroup of upper triangular matrices, non-degenerate, and which I denote by B. B stands for Borel. So I have my Borel subgroup inside GLV, and I have my flag variety, which is a homogeneous space GLN over B is my flag variety. Okay, so well, from this you can just find the dimension of this variety. It's the dimension of GLN minus the dimension of this thing. So this is n minus 1 over 2, or n choose 2, which is the same. Okay, and so this is the space of all possible flags, and you want to do computations in its cohomology ring, and for this, well, sometimes it's useful to have a cellular decomposition of a manifold or of a variety you're working with, and such a cellular decomposition exists, and it's given by some very nice conditions. So, well, I can say that upon this variety, I have another group acting, another subgroup of GLN. Namely, I can say, well, it's not interesting to act on by upper triangular matrices. Let me, from the right, let me act by lower triangular matrices from the left. So B minus will be the set of lower triangular matrices, and B minus acts on the flag variety, and I'm considering the decomposition of the flag variety into the orbits of this action, or equivalently, I can start with the decomposition of GLN into something like B minus times MW times B, where W is permutation, and I'll tell you in a minute what this is. So suppose you have a non-degenerate matrix. Well, you know very well that for a generic matrix, you can have what is called LU decomposition. You can present it as a product of an upper and lower triangular matrices. Well, but this only holds if you have some conditions on the principal minors, and if you want to avoid this, you can just say that, well, you can multiply your lower triangular matrix by from the right by a certain permutation matrix. MW is, it consists of zeros and ones, something like that. 1, 0, 0, 0, I don't know, well, something like that. You have a permutation of basis vectors. And your GLN is presented as a disjoint union of these double cosets, and your flag variety is presented as a disjoint union of these orbits, B minus MW B mod B. And I denote these by omega W, and these guys are isomorphic to affine spaces, C to the power L of W. And they give me a cellular decomposition. So what's the dimension of this guy? No, I'd rather want here. I have. I'd like to have some dimension D, where how to find the dimension of of this guy? Well, you need to compute some stabilizer, and after you do that, you see that this d is equal to the dimension of your flag variety minus the length of your permutation, W, well, the permutation which comes from this permutation matrix. And the length of the permutation is the following thing. It's the number of inversions. It's the number of pairs of elements which are put in the wrong order. So this is the number of pairs ij such that I less than j and w of I greater than w of j. Okay, so these guys are cells. They are called Schubert cells. And you can also consider their closures. X w, which is omega w bar. They're called Schubert varieties. And they arise in enumerative problems. And say, for example, if your W is the identity matrix, then your Schubert cell is open, right? Because a generic matrix has an LU decomposition, and so the flag variety is the closure of this omega identity. So X identity is the whole thing, and if you take W naught to be the longest permutation, where you change the order of the elements completely, like read your line from right to left, then you have x omega naught to be, well, this is just b then. So this is just one point. Let's say b mod b. This is a point. Okay. So far so good. So, and these Schubert varieties, they have some very nice properties, and well, in these 2 weeks we're here to speak about these properties. So they're related to a ton of things in combinatorics and representation theory, and today I'll be speaking about enumerative geometry. So I'm interested in the cohomology ring of the flag variety. Yeah, it's just the closure of Schubert cell. Oh yeah, of course, yeah. So so you can well, this is a cell decomposition, and the closure of each cell is a union of cells, right? So XW, you can say that XW is the union of some omega V, where V is less than or equal to W, and so you get some, in this way you get some geometric order on the symmetric group. And this is called the Bruhat order. And it can be described combinatorially. Of course, it has a number of quite simple descriptions, but it's not the topic I'm interested in today, but it's also something worth looking at. So what I'm going to say now, that I can consider the homology and cohomology ring, because flag variety is smooth and I have Poincare duality. So let me speak about H upper star. And H upper star is generated as an abelian group by the fundamental cycles of these Schubert varieties. So its dimension is with everything is with integer coefficients. So the dimension is n factorial, and well, this is graded, and also you have a ring structure. The ring structure is, this means that you have multiplication, and multiplying things involves some structure constants of this ring, and you are interested in describing the product on this variety. So xw times xv can be decomposed into the sum cwvu, where times xu, where well, u is just some other set of permutations, and these structure constants are called Littlewood-Richardson coefficients. And describing them is a very interesting and open problem. Well, I mean, describing them combinatorially is an open problem. Some pretty simple geometric argument can show that these coefficients are non-negative integers. This is implied by Kleiman-Bertini transversality theorem. These structure constants are non-negative, and if you have a non-negative integer, you would like to find its combinatorial meaning, right? And say if you consider the same problem for Grassmannians instead of flag varieties, this is what one or maybe two courses on this school were about. How to consider what is the set that these that has CWVU as its cardinality, right? So what do these numbers count? Okay, for Grassmannians, it was done by Lascaux and Schützenberger, and that's why it's called the Littlewood-Richardson rule. Okay, and for flags, this is considered to be open. I put a question mark here because there is a series of papers by Josh Kuhn on what he calls Mondrian tableaus. And Mondrian is not a mathematician; it's a Dutch Dutch artist who, well, one of the pioneers of abstract art, who had pictures with some squares, lines. Well, the squares have different color. Well, it was about the form and the color. So some abstract art. Google if you're interested. And Josh Kuhn's combinatorial objects are also unions of squares and something like this. So that's why he calls them Mondrian tableaus. But the combinatorics is extremely difficult, and like there is no agreement in the math community if this is this is right or wrong, or like this. So this is like still considered to be open. Okay, so. Yeah. It's on archive, but it's there is a paper by Josh Kuhn about two-step flags, which is published in Invenciones, and I think about maybe 7 or 10 years ago. But the flag case, like no one really understands it. So my goal for today is to find a different approach to Schubert calculus. But before I do that, let me just show you some small example. How does this multiplication in the cohomology ring of flags work, and why it is just some manipulations with some simple geometric objects. So here's my example. Let n be equal to 3. So I'm considering V1 inside V2 inside C3 vector subspaces, or otherwise I can say that I'm considering everything projectivized, and I'm looking at a point which sits inside a line, and the line lives inside the plane P2. And I'm interested in mutual position of two objects consisting each of a line and a point on it. So my complete flag is something like this. And if I have two complete flags, well, here I'm describing mutual position of two flags, one fixed and one moving. And let me say that if my permutation W is the identity, then I have these two flags in a general position. And if I degenerate this picture in one way or another, I can get something like this. For instance, where the subspace of moving flag passes through this fixed point. All right, so and this will be called the permutation S1, which is 2, 1, 3. S1 because it's the first simple transposition. It interchanges 1 and 2. Okay, and if it's vice versa, if the red dot is on the white line, then I call it S2, which is 1, 3, 2. Okay, I can degenerate it even further. Say I can bring the red point into the white one. So I get something like this. And this is my permutation S1, S2, which is 2, 3, 1. So 1 goes to 2, 2 goes to 3, 3 goes to 1. And another way of degenerating this configuration is let me rotate the red line around the red point to make these two guys coincide. That's it. And this is another permutation of length 2, which is 3, 1, 2. Okay, and the most degenerate configuration is where these two flags coincide. This is S1, S2, S1, or S2, S1, S2. This is 3, 2, 1, as I explained here. Okay, and now let's do some intersection theory. We'll do it as follows. Well, let's take, this guy, and these are two flags, and I'm describing their mutual position. And yeah, these numbers, this permutation is constructed according to certain rules out of this configuration. These are just some. No, I don't want to go much into that, but here's the explicit definition. So yeah.
That's just the permutation of the moving flag.
Okay. Yeah, and yeah. So let's now do some intersection theory, and let's compute the square, say, of this guy. S x s1 squared. So what does it mean? I have, let me say that I have two flags in general position. I have my two fixed flags, and I'm now interested in the flags which are in the same position as prescribed by S1 to the white one and to the blue and to the yellow one. So this, so the red line should pass through the white dot. On the other hand, it should pass through the yellow dot. So this means that the red line is fixed. And the red dot, well, it can move around. It can be anywhere. But what does it mean that the position of my line is fixed and the dot is moving around? This is exactly this condition. So what I get is x s to s1. Here it is. So this case is pretty simple. We can do the intersection just by bare hands and not degenerating anything. Okay, but in other cases, of course, it's more complicated. Even if you want to multiply these two guys, you'll get the sum of these two guys, but that's not that easy. And what I'm going to speak about now is some other approach to multiplying Schubert cycles. Okay. So what I'll need now is the notion of Gelfand-Zetlin polytope. Okay. Okay, Gelfand-Zetlin, or GZ for short. Zetlin is sometimes spelled as with Z or C or TS. You can see all three versions. Okay, let me start with a sequence of, with an increasing sequence of n integers. And now I'll write down equations for a certain polytope, which will be called GZ of lambda. It will depend upon this sequence lambda. And it will live in the space of dimension n times n minus 1 over 2. And so it will be as follows. Let me draw a, well, maybe let me put lambda 3, lambda n. And let me draw a triangular array, x1, 2, x1, 3, etc., x1, n minus 1. This line is shifted by half step. And here I have x1, 3, x2, 3, x2. No, I'm starting with x1, 1, sorry. x1, 2, etc. And here it's x2, 1, x2, 2, etc., x2, n minus 2. At the last row, I get xn minus 1, 1. Okay, that's a triangular array, and I'd like to impose the set of inequalities. Namely, once I have three numbers a, b, and c, I am saying that a is less than or equal to c, less than or equal to b. So x1 is between lambda 1 and lambda 2. x2 is between these two guys, x21 is between these two guys, and so on. Okay, such polytopes or such arrays of integers appeared in the 50s in a paper of Gelfand-Zetlin where they constructed bases for representations of GLN. Okay, so in this case, there is one case where you can just make a picture. It's n equal to 3, and in this case the dimension also equals to 3. So if you take a, b, c, and x, y, z, then you'll get the following thing. You'll get such a magical crystal, which is just an infinite prism cut by two planes intersecting on its edge. So it's this horizontal section is a rectangle, and yeah, so z is going upwards, and and you see that it's a polytope, but the polytope is quite bad. It's not simple because, say, here in this, well, simple polytope means that in each vertex you have the least possible number of edges meeting. Like cube is simple and an octahedron is not. So here, this guy is not simple because here you have not 3 but 4 edges meeting in this point. So this is a bad and nasty vertex which gets in much trouble. Okay, but so we got this polytope, and what we are going to do is as follows. To each phase, our program is as follows. To each Schubert cycle, you assign a combination of phases of the GZ polytope. So XW, you assign some collection of phases of GZ of lambda. Then you impose some relations upon phases. This means that each phase can be XW can be presented in different ways by using these relations. So impose relations upon phases. And then you want to do it in such a way that the, well, let me call this collection, well, union of phases, union of gamma wi. And then you would like to have the product to be corresponding to the intersection of these unions, just like you do in the toric geometry. Yeah. This guy should be gamma wi intersected to union of gamma vj, provided that the gamma wi and gamma vj's are transversal. Well, basically, it works very much like toric geometry. In toric geometry, you have a variety with an action of a torus, and you have T-stable subvarieties, and they correspond to phases of certain polytope. So it's called the Newton polytope, and the intersection of these varieties corresponds to the intersection of phases, just like in this case. But the flag variety is not toric. So that's why you need to take unions of faces instead of just individual faces. But yeah, what you can do is toric degeneration, but then it won't be smooth. So, oh,
Is that to multiply Schubert function?
Just wait a minute. Wait a minute. So Schubert functions will arrive shortly. What is well, let me tell you how are we going to carry out this program? What can we assign to a Schubert class? So, next question is how to assign a collection of faces to a Schubert class XW. Okay, let me give names to these faces. Let me denote the two ones which you don't see by gamma 1 and gamma 2. These are on the back. And those on the front, I'll call them F1, F2, F3, and F4. Okay, these edge, the vertical one will be called E2. And this one over here, it will be called E1, and I won't need the other ones. And now let me carry out the first step of this program. Let me assign collections of faces of the GZ polytope to permutations. First, I'm going to do it in other way around. I'll assign permutations to faces. How do I do that? So what is a face of my Gelfand-Zetlin polytope? A face, well, means that here you have a bunch of inequalities. A face means that some of them become equalities. Like this is an equality and this is an equality. So this defines you some face. Well, a bad thing is that some of these equalities may imply the others. So if this guy is equal to this guy, then so if these guys are equal to that one, so the guy under them is between. Well, there is an inequality that this x over here must be between these two, so it should be equal to both of them. And well, that's well, but I'm going to consider faces where this doesn't happen. Namely, I'm going to consider the faces only with equalities of this type, not of that one. Okay, so I'll depict faces by diagrams of the following type, like this, and I don't know that. So so this is my GZ pattern, and I draw these edges in bold if I impose equalities. So such a diagram represents a face of my polytope.
What is lambda?
Lambda is just some collection of integers. Lambda i's are integers, and they somehow they are responsible for the metric size of your GZ polytope. If you
What do you choose then?
I care only about the combinatorics, not about the metric size.
So they could be real numbers.
Well, I'd like, let them be integers. Of course they can be reals, but let them be integers. I'll tell you why later, because it's good to have sums over integers, right? So you'll get some characters. Yeah, you would get some characters. Okay.
So there's two types. Just think about the equality there. So there's two types of edges.
Yeah, well, there are two types of equalities, like this one and this one, right?
Oh, okay.
And I'm only imposing those going northwest, southeast. Okay, this means that, if I impose these equalities, I'll get a face which will contain the face corresponding to all those equalities imposed at the same time, right? And this is that vertex. So this means that all my variables are the least possible. Got it? Oh. Okay. So let me.
So why are you marking two things? I mean, why are you having two types of edges? That's just.
This is an equality I am imposing, and this is an equality I'm not imposing. No.
Okay.
So this is some face, right? Some face containing P. Well, let me have this P, and this is some face containing P. Well, some of these equalities are still there, and some of them are relaxed.
What are your inequalities?
Well, these are inequalities on the GZ pattern, and some of them became equalities. That means that I have moved to a face of my polytope.
So every time you impose equality, you're moving to one dimension lower face, basically.
Yeah.
These are independent. So you say these are all independent.
Yeah, these are. If I only consider those, they are all independent.
And then choose two of them. So these give you change in the face.
Right, of course. In fact, you'll see a little bit more now. So let me put simple transpositions on these edges in the following way: S1, S2, S2, S3, 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 and then let me read this word from left to right, but from bottom to top. So for this particular face, I get a word where Si is, as usual, S, the transposition of I and I plus 1. And this particular word is, I'm reading it like this. This is S2, S3, right? And this word is reduced, meaning if I multiply all these transpositions, I'll still have a permutation of length 2. So this is a reduced word. And it gives me a permutation S2, S3, which I call W of F. So if my word is reduced, then I'll also say that my face is reduced. If the word is reduced, then F is also said to be reduced. There are non-reduced faces, like if you take, say, this edge, it corresponds to the following thing. It corresponds to S2, S2, and this is a non-reduced word. And those of you who have attended or maybe gave courses last week probably recognize pipe dreams. So this construction can be brought easily to pipe dreams. Okay, so And now, if I'd like to go the other way around, I'm starting with a word, and to this word, I assign. I'm starting not with a word, sorry, but with a permutation, and I assign the collection of faces, of reduced faces, with this word. So from W, I get a collection of faces, UFWI, such that FWI is reduced.
Reduced faces are 5
Yeah. So FWFI is reduced, and W of FWFI is exactly what you need. So let me see how things work in this example. So say for the identity, this is the GZ polytope itself. For 213 for S1, the only reduced face is where x equals a, right? So the face where x is minimal possible, so it's gamma 1. So this is gamma 1. And say for this guy, there are two possibilities. It can be either this S2 or that one. So this is F3 and F4.
What are the directions X, Y, and Z over there? It's a bit confusing. E1, E2 are X and Y.
What are
Picture.
oh here?
No, in the picture of the polytope.
E1, E2 are edges.
X and, what is X and Y directions?
As usual, X, Y, Z. Okay. So, yeah, and say this is E1, and this is E2, and this is the point P. Okay. Now I can already do some computations, but before I do that, let me carry out the second step of my program. Let me impose some relations upon faces. Let me do it in the following way. Take my polytope and shift it slightly up and down along, say, the z-axis. When I shift it up and down, I remove slice which looks like this face, and add a slice which is like this face. So in this case, I impose the relation F1 equals F3, because removing, if I preserve the volume, that means I'm removing F3 and adding F1, or other way around. If I shift it towards the x-axis, I'll get the equality gamma 1 equals F2 plus F3. And finally, if I move towards myself, I'll get F4 plus F1 equals gamma 2. Okay. And let me finally do some computations. So I'm claiming that this allows me to compute things, to compute Schubert cycles. To each Schubert cycle, I can assign a combination of phases. Here is how I do that, and here's the procedure. And and I impose the relations, and this is something I have done in the three-dimensional case, but it's also simple. You can carry this out in arbitrary dimension. Let me see how things work. Let me multiply xs1 by xs2. Okay, so this means I should take gamma 1 and F3 plus F4, gamma 1 intersected with F3 plus F4. And this is gamma 1, this is F4, this is F3, and the intersection is E1 plus E2. And this is the sum of two Schubert curves. So back to our dictionary, E1 is here, E2 is here. So this is X S1 S2 plus X S2 S1. Okay. Let me compute X. I don't know why did I put the upper index. If I compute the square, this is intersecting gamma 1 with itself. But this means I need to impose relations. Gamma, sorry, if I'm, yeah, it's probably the other way around. It's U1 and U2, yeah, like this. Yeah. So if I multiply this with intersected with itself, this means I get F2 plus F3. Gamma 1 and F2 do not intersect, so the intersection is 0. And here I get E2. So here I get E2, and this gives me X S2 S1, just like in this case. Okay.
So why did you mark E1 and E2 there? With what?
E1 and E2 are edges.
They're edges of the polytope.
Yeah, so E1 means that Z is arbitrary, yeah, and E2 means that Y can be arbitrary, and so so E1 is something like that. This is E1 and this is E2. Okay. Okay, so that's how we do computations, and so let me state this as a theorem. So the map from Schubert cycles to unions of gammas defines ring isomorphism where the multiplication corresponds to intersection. And one more thing is that you can, from this presentation as a Gelfand-Zetlin polytope, you can find some numerical invariants of your variety. So today at the class we have computed the degree of the Schubert of a Grossmanian. Let's now compute the degree of a Schubert variety in the flag variety. So if I have my set of weights lambda, this defines me a representation of GLN V lambda, and if they are all different, then I have an embedding of my flag variety into its projectivization, right? And I'm claiming that the degree, say, let me take some Schubert variety inside here. And it's embedded into the projective space, and I'm trying to find its degree. Its degree under this embedding, because it depends upon the lambdas, of course, is the volume of the set of faces understood in the following way, that each identity square is considered to have volume 1, volume of the union of faces, f wi, times certain constant, d minus L of w factorial, where d is n minus 1 over 2. And one more thing is that if you're taking this representation of GLN, then you have de Mazur modules, and de Mazur characters are also obtained as sums on the collections on corresponding faces. But my time is up, so I cannot tell you about this. Thank you.